So next one is okay. So part D is yes. So okay. Before moving to part D, so here we saw that the smallest number where all primes are different. So PQ and R all primes are different, 3, 5, and 7. Then the smallest number is 420, right? But the thing is this 420 is the smallest number such that we can have 4 different factorization, or can we make it even smaller? So they are asking for the smallest number, right? In part
In
C.
part C.
Right. In part C, we did that first part we did, right? So smallest number in which 2 different factorization as product of p primes, that is fine. And then the last part is saying that find the smallest number with 4 factorizations, right? So yes. So if PQ and R are different, then it is fine. We have 4 factorizations. But the smallest number what I get is 420. But the question is this is the smallest, or can we create something smaller that will have 4 factorizations? Right. So
But
for that, yes.
uh, but we need one letter more. We only have 3 letters.
No, no, need not be, right. So for example, if we consider this type of number, so for p cube q, where p and q are odd primes, right? So if I consider this number, so how many factorization here we have? So here we have 2p into 2q, then 2p square into 2pq. So 2p into 2p square q, right? And
Okay.
finally we have 2 into 2p cube q, right? So this also have 4 different factorization, right?
Okay.
So here p is not equals to q. So these are 4 different e prime factorization. Right. So then the smallest what you can create is when you choose p equals to 3 and q equals to 5, right?
Yes.
So what is the number?
And the number would be 27, 540.
Right. So 4 into 3 cube into 5. So this is 540, right? But this is bigger than this 420, right?
Yeah.
So this will not work. But this also have this type of numbers also have 4 factorizations, right? 4 prime factorizations, right? And next one is if I compute this thing, 2 cube p square cube. So here it is going above because we are multiplying 3 cube, right? So that's why it is going above 420. So here instead of 3, if we choose one more 2, right? Okay. So this also have, so this you can so this also have 4 different factorizations that we can check. So one is of course 2 into 2 square p square q. Then we have 2p into then 2q into p square, right? And finally we have 2p square into 2 square q, right? These are the 4 factorizations, right? And here if you take p equals to 3 and q equals to 5, then n equals to, so I think this is 360, right?
Yeah.
So this is the smallest one. So n equals to, so this is less than 420. So it is the smallest number.
Yeah. So you
With,
choose 2 to the cube because you can have
right. So the thing
4
is,
and 2.
yes, yes. So here 4 is already needed. Then I am taking 2 into p square into q. So this is the thing I am taking. So to reduce the quantity, so here we want p cube, right? So if I replace p by 3, then it is going over. So that's why instead of 3, if we take 2, so that I verified whether it is smaller than that or not.
Mm-hmm. Yeah.
So it is the smallest number with 4 different e prime factorization. Okay,
Mm-hmm.
right. So now, so part D that they are asking. Part D asking is, okay, so the number 12 has only one factorization as product of e primes, right?
Mm-hmm.
So it is 2 into 6. Then they are asking describe all even numbers that have only one such factorization.
Describe all even numbers
Yes.
that have
That have
if
only one factorization. As product of e primes. Right. So you have to understand then what is the condition, right?
all even numbers that have one factorization. Mm-hmm.
Right. So the thing is, yes. So if it is already an e prime, then there is only one factorization that we have done. So other than e prime, we have to think what is possible.
All even. So even means that if you divide 12 by 2,
Yes.
that 6 is it is a part of the E sum, right?
Yes, is e prime. So 6 is an e prime, right? Because it is, if you divide by 2, it is an odd number. So it is an e prime.
So before we did, if we want to find all the E primes,
Yes. Yes, we
we
find all the e primes, right?
so what we did is we divide by 4, right?
No, no. The thing is, if we divide by 2 and it is an odd number, then the number is an e prime. That is the characterization we did, right?
Right. If you divide by 2
Yes,
and
and it
then
is
you
an
get
odd
an
number,
odd number, that would be an E prime.
right?
But if you divide by 4,
Yes.
so it must be a multiple of 4.
Yes, yes. If it is not an e prime, it must be a multiple of rho. Yes. But the thing is, in this, what they're asking, they're asking that it has only one factorization. So if it is an e prime, then it is fine, right? So it only have one factorization, right? So that is fine. Means we have to find outside e primes what numbers, what which even numbers satisfy this condition.
So all E primes don't have more factors, right? Because they are already primes.
Yes, yes. So yes. So the
So
thing is, e primes.
we can maybe just describe them as a multiplication of two E primes.
Yes, but the all type of things will not work, right? Because we can arrange them, right? So if it is a product of two e primes, then we can arrange them in a different order, right? So for
Sorry.
example, yes. So for example, 6 is 2 into 3. So next is suppose you are taking 2 into 5. So suppose I am constructing a number that is 6 times 10, right?
Mm-hmm.
So this is an a factorization in E prime, right?
Yeah.
So but this I also can write 2 times 30, right?
2 times 30, right? That's
This
another
is also
factorization.
this is also an E prime factorization, right? Because 30 is 2 times 15. So both are E prime. So this number will have two factorizations. So that they are not asking, right? So this will not work. So they are asking they to have only one factorization.
Right.
So we
Okay.
need only one factorization. So it should, yes.
So that means that if you have more factors, like um, because 6 is 2 and 3, and 10 is 2 and 5,
Yes,
then
yes.
you can rearrange the
Yes, yes, yes.
factors.
So that is the thing. So you cannot have more than one odd term. So here 3 and 5, two odd primes are there. So if we rearrange them, we will get another factorization. Yes. So that is the idea. So the number, so if the number is of the form some 2 power r, right, times some prime number, right.
Mhm.
So then we will have only one. So we'll have prime factorization, right? So only one e prime factorization. That is 2 into 2 power r minus 1 into p. Or you can do the other way around. So here, if r is greater than equals to 2, right?
Mhm.
Right. Then will it have exactly one e prime factor?
But if okay. So 6 multiplied by 10, we have 2 and 3, and then 2 and 5.
Right, right.
So we have two p's, 3 and 5.
Yes, yes. Two odd primes we have.
So since we have two p's, that will not work. We only need one p.
Yes, yes. We only need one p.
So it doesn't matter the amount of tools we have.
Yes, yes.
Okay.
Right. And also, what we can have is also we can have n of this form only 2 power r, where r is greater than equals to 1. So this also will have exactly one factorization as e primes.
E primes.
So it does not have
Mm,
any other factorization, right? So we have to write like this only.
but 2 to the r multiply p is different than 2 to the r only.
Yes, yes. These two are different. Yes, yes.
But they both satisfy the
Yes, tell.
the condition. They both satisfy the condition.
Yes, they both satisfy the condition.
Okay.
Right. So the numbers are this type of numbers. So the last number is 2 times k, where k is odd. So this is an e prime, right? So if k is any odd number and 2 times k, so that is already an e prime. So it will have only one factor. So this is the one factor.
Okay. Odds. Yeah.
Right.
Okay. Odds. But 6 would be an odd number.
6.
Yeah.
No, 6 is 2 times 3, right? So 3 is an odd number. So 6 is an e prime, right?
Yeah, but I mean, you said in the last line you said okay odds.
Yes, yes.
So
2 times k.
2. Yeah, but 6 is not an odd number.
No, 6 we don't need. So 6 is so n equals to 6 will work. That is I'm saying. So if I take n equals to 6, so it is 2 times 3, right? So this will work in this set because it has only one
Mm-hmm.
factorization. That is 6 only, right?
Mm-hmm.
Yes, that is what I'm saying.
2 multiply 5 will also work.
Yes, yes.
So you need those. You're saying you need those three n to
Yes,
describe.
yes, these are the three type of n that will have only one factorization. So that is what I'm saying.
So we need these three n
Yes, is any
to.
so they asked to describe all the numbers, even numbers that have only one factorization, right? So these are the three class we have.
Okay. Mm-hmm. Yeah.
Okay.
Yeah.
Okay. So the next one what they're asking is so next one is 6. Right. So they are defining another thing. So that is called M world. So where the numbers only numbers that exist are positive integers that leave a remainder 1 when divided by 4. That leave a
Mm-hmm.
remainder divided by 4, right?
Mm-hmm.
So what will be the set? So it will be 1, 5, 9 like this, right?
Mm-hmm.
21 and so on. Right. So the thing is we cannot. So if you see the things, so the number a general number. So suppose n belongs to this m. So n is of the form 40 plus 1, right? For
Mm-hmm.
some t.
Yeah.
Right. So the thing is you cannot add numbers, right?
You
So
cannot
we
add them like 9
uh,
plus 5
right. Why we cannot add them?
because they are not the multiple of 4 plus 1.
Yes, 9 and 5 they're individually of the type 40 plus 1, but after adding them, that will not be left, right?
Mm-hmm.
So if you take n1, that is 41 plus 1, and n2 is also of this form 42 plus 1, then n1 plus n2 is 4 of t1 plus t2 plus 2, right? So that does not
Mm-hmm.
belongs to m. So hence we cannot add number, right?
Mm-hmm.
But why we can multiply them?
You can multiply them because
Yes. So what happens if I do n1 times n2? So that is 41 plus 1,
mm-hmm.
42 plus 1. Yes. If we multiply them, then
16 times T1, T2,
right,
then 4 times T1, 4 times T2,
plus 1, right? So this is
plus
4
1.
times some t3 plus 1, right? So that belongs to m. So multiplication is allowed, right?
Yeah.
Okay. So next they are defining. So we say that m small m divides n if n equals to m times k, where this k belongs to this set m. Okay.
Where K belongs to M, okay?
Right. And same thing. So if n is a m prime, if its only divisors are m divisors are 1 in itself. Right. So they are asking to find the first 6 m primes. So from this list, we have to find the first 6 m primes.
The first 6 primes, I mean, just guessing.
No, we have to satisfy the property, right? So only the divisors are 1 itself. So yes, so the first 6 primes will be easy because the numbers are small. So 5 will work, right? So 5, there is no m divisor, right? It cannot be divided by anything else, right?
Yes.
So
But
same
9
with
as well, right?
right.
9,
Hmm.
13, 17, 21,
Yes.
like all of them.
Yes, no, yes, up to 21 it will work. But okay, let me tell you. So what is the next number in the list after 21?
25.
Right, then?
And 25 could be divided by 5, right? 25,
Yes,
29.
25 will not work. That's why. So the thing is, so 5, then 9, yes, 21, and then one more we have to find. So that is 29 will work, right?
Mm-hmm.
Right. So these are the first 6 m primes. So that is fine. So part B, they are asking, find an m number n that has 2 different factorizations. So right. So when will we have 2 different factorizations?
That has 2 different factorizations as a product of n primes.
Right.
So, I mean, we can have find an m number. So what makes an n number the form 4t plus 1? That
Yes,
makes
yes,
an
that is an
n
m
number.
number. Yes, 40 plus 1.
And then 2 different factorizations would
Right.
be 41 plus 1 and 42 plus 1.
Right. But 2 different factorization as a product of m primes. So the product should be the individual elements should
Only
be m primes.
n
Yes.
primes.
Yes.
Oh, yeah. It's a product of n primes. Okay.
Okay. So let us see some few numbers. So 9. Right. So let us see. Okay. One observation is so these numbers except 21. So 21 is not prime in our usual sense, right? But it is prime here. But other
Yeah.
than that, 5, 9, 13, 17, and 29. So these are prime in our usual integer sense, right?
Yeah.
Okay. So let us see some few more numbers. So 9 if I take, right? So 9 we are taking from here. So this is 3 times 3, right?
Mm-hmm.
This is an m prime. So next is 21 if I take. So that is 3 times 7.
3
So
times 7, okay.
so this is also an m prime that we saw. And 49 if I take. So that is 7 times 7. Right.
Mm-hmm.
So this is all of them are m prime, right? Because 7 does not belong to this list. So this factorization does not work here. So 49 is also an M prime, right? So now, if I want to construct a number that has two different factorization, right? So of M primes. So that is we can manage with 3 and 7, right? So if I manipulate like this, so if I take 9 and 49, right? So it has 3 square
Okay.
and 7 square, right? So so if I take 3 square times 7 square, so this I can write as 3 times 7 times 3 times 7, right? Also, right? So yes, so this is nothing but 21, right? 21 times 21, right? So the number is, I think, 441, right? So the 441 is the number that I can write in two things, right? So it is 9 times 49, and also it is 21 times 21.
21, 21, and
So
9
21
and
also is an E
49.
prime, right? 21 is an E
Right,
prime,
and 49 as
and
well, right? Yeah.
right, 49 as well, that I saw, and 9 also belongs to the list, right? So this is the number we can create. But why this is the so why did it work is, so the thing is, if I see the list, so in this list 3 and 7, these two prime numbers are missing, right?
Yeah.
So like this, so that's why we can construct these two type of multiplication, and still that will work, right?
So you're also saying that we can derive the M numbers by using 3 and 7.
Yeah, no, tell again.
We can get the M numbers from 3 and 7.
Yes, 3 and 7, no, we can no, here we are actually trying to find a specific type of number, right? So that has two different factorization as M primes. So that we can construct like this, right? Okay. So similarly, we can construct another one like this as. So the next number that is not on the list, the next prime number is 11, right? So the 11 is not
Okay.
in this list, right? So
Yes.
what you can do is, so if I take the prime number 3, 7 and 11, right? So if I take these three things, then what I can do is I can make 3 square into 77. So 77 is also 4k plus 1, right?
Right.
Because 76 is divisible by 4, right? And then I can do I can take in 3 and 7. So I'm taking 2, 3 and 1, 11, right? So 3 and 7 is 21 that I can take, and 3 and 11 is 33. So that is also 4k plus. And now since 3, 7, 11, they are not in M, so these things will work. So this is, I think, 693. So 693 is another number that can be written as a product of two different factorization as a product of M primes. So like this we can construct.
Okay. Okay, so for 3 and 7, you're saying we can keep increasing the power of 3 and 7, and we will
Yes,
keep
yes,
finding more M primes.
right. Because 3, 7, 11, these primes are not in the list of M primes. So, but we can suitably choose them such that after doing the product, that belongs to that 4 elements, that belongs to M, because the individual elements must belongs to M, right? That is of the form 4 T plus 1, right?
Okay. Well, this is just a coincidence that 3 and 7 they give you m primes.
Yes. So that so this idea comes from the seeing the initial list, right? So here you have 3 times 3, 3 times 7. So that is a prime number, right? So that gives you an idea that it will work, right?
Okay.
So similarly, if you take 1, 3, so if you take a single 3, 2, 7, and 1, 11, if you take these phone numbers, right? Then also you can construct. So if you take 3 into 7, that is 21 and 77, right?
Mm-hmm.
And on the other hand, if you combine 3 and 11, you get 33 and 49. So this is 1617. So this is another number that you can write as two different prime factorizations.
Two different prime factorization. And there are no more combinations, right? I mean, you combine it differently and you get the same two.
Yes. Other combination is not available, right? Because you have to choose two of them, right? Otherwise, you will not get these things.
Uh-huh.
So either you can choose 3 with 11 or 3 with 7. So these are the only two options you have, right? Because this number is repeating, so there is only two options.
Uh-huh.
Fine.
Okay.
Right. So this is fine, I think. Okay. So the next question they are asking is,
So there is no generalization for this.
no, they are just asking to find a number that is two different factorizations. Okay.
Uh-huh.
Right. So next one is some they're asking to write a program that you can see later. So means exercise 7. Right. So we can move to the next chapter. So the next chapter is on congruences. Chapter 8. Okay. So what you have is so this notation you may know. So A congruent to B mod M. So this will say if and only if M divides A minus B, right?
Mm-hmm.
Right. So for example, 7 is congruent to 2 mod 5, right?
7 is congruent to. Okay. Yes.
Right. So similarly, 47 is congruent to 35 mod 6. This is also true because 47 minus 35, that is divisible by 6, right?
So you're saying 47 divided by 6.
No, 47 minus 35, that is divisible by 6. This is the definition, right? So we'll say A congruent to B mod M if and only if M divides A minus B.
If n divides the difference between these two.
Right.
So when you say divides means it's a factor, right?
Yes,
There is
divisible, yes, factor.
no
So
there
6
is
is a factor.
no rest. Okay, so 47 minus 35
Yes, how much
would
is that?
be 12.
Right.
6 divides 12. Okay.
Fine.
Uh-huh.
So in particular, if A divided by M, suppose it leaves a remainder R, remainder of R, then we can say that A is congruent to R mod M, right? So since remainder is R, we know that R is strictly less than M, right? That is the definition of a remainder, right?
I minus R and divides I minus R. Okay.
Right. So how does it looks like? So since we have remainder R, so A must look like this, right? So A equals to M times Q plus some R, right? Where Q is the quotient, right? So when you subtract, then it becomes MQ, right? So that's why we
Yes.
can say that M divides A minus R. So from that it follows that A is congruent to R mod M.
And divides I minus R. Yes.
Right. So yes. So what are the remainders possible when you divide by R? So what are the possible remainders? Sorry, when you divide by M, what are the possible remainders? So yes. So for example, you can think of an example. So suppose if I divide by 5 any number, so what are the possible remainders there?
Oh, from 0 to 4.
Right, right. So 0, 1, 2, 3, 4. All of them can be things. So when I divide by M, the possible remainders are 0, 1, 2 up to M minus 1. Right. So from this argument, what I get is every integer. So every integer is congruent modulo M to some number between 0 and M minus 1, right? To a number between
Every
0,
integer is congruent.
right? It is congruent to modulo M. So when I do mod M, so it is congruent to any one of these numbers, right? 0, 1 up to N minus 1. So should I show you an example or is it clear?
Yeah, an example.
Right. So what I'm saying is, so same thing. So let us take M equals to 5, right? So if we have this set of integers, right? 0, 1, 2, 3, 4. So this is the set of remainders. So now you take any number. So suppose I take 10, right? So 10 is congruent to 0 mod 5, right? If you take 12, 12 is congruent to 2 mod 5. You take anything. So you take 16. 16 is congruent to 1 mod 5. So any integer, it should be congruent to any one of these 5 elements. So that is what they are saying.
So when you made the definition,
Yes, tell again.
so when you define the congruency, you include 3 variables: A, B, and M.
Right.
Or M, right? A, B, and M.
Right.
So you're saying any number is
Okay.
congruent to 0, 1, 2, 3, 4, and 5.
No. So when I'm taking M equals to 5, then any integer. So any integer is congruent to any one of these elements: 0, 1, 2, 3, and 4.
So any number that would be A, right? A
Yes.
would be congruent to B mod to be mod M, but in this case B is 5 and
No, no.
mod
M is
N.
5. B is any number of this set from this set. Any B can be anything from this set. So what are we saying is
any A.
So A is congruent to B mod 5. If I take this, then B must belong to this set 0, 1, 2, 3, and 4.
Okay.
Right. So A can be anything.
Okay.
A belongs to any integer.
Yes, A is any number. B is any of those, and M5 mod 5. So B, you said also is like the reminders, right?
Yes, B is the remainder.
Yes, like the reminders. Okay.
Fine. Okay. So approach is fine. Then okay. So the next we'll have some operation. So they're saying that congruences with same modulus. So if I take congruences with same modulus. So for example, if I take A1 is congruent to B1 mod M, right? And another congruence I take A2 is congruent to B2 mod M.
Okay.
Right? So then if I add and subtract, that will also work. So that is what they're saying is A1 plus minus A2. You can do anything. So that is B1 plus minus B2 mod M. Okay.
Okay.
And if I do the product, A1 A2, that is congruent to B1 B2 mod M. So that will also work.
Yeah.
Right. So why it is working, let us see. So the thing is so from the first equation I have that M divides A1 minus B1, right? And from the second one I have A2 minus B2, right? So A1 minus B1 equals to some MK1.
Okay.
This is some MK2, right?
Right.
Then if I add them, so that is also M times M K1 plus K2, right? So this implies that M divides A1 plus A2 minus of B1 plus B2, right?
Yeah.
So A1 plus A2 is congruent to B1 plus B2 mod M, right?
So you're saying A1 plus A2
Right.
would be right. Yeah. Okay.
Fine. So similarly, we can do the subtraction also, right? So here, instead of addition, if we do subtraction, same thing will work, right? So then it will become A1 minus A2 minus of B1 minus B2. So then you will get this subtraction thing, right?
Yeah.
So what about the product? How it will work?
I mean, we can do the same, right? A minus 1A, the product. Yeah, I mean we can do the same maybe, and then we can see.
Same, how will you do?
That would be a minus a1 minus b1 equal to nk1,
Right.
a2
Yes.
minus
Up to
b2.
yes, up to this is fine. Then how will you go to the product thing?
So we need to multiply a1 and a2.
Right.
I mean, we can multiply them both.
Okay.
We will have a1, a2,
Right.
will be a1, a2 minus a1, b2.
Minus
A1, a2
A1 B2. Right.
minus b1, a2 plus b1, b2.
Okay.
Um, mm, maybe we can like factorize.
No, we already got from the factorization, right?
So we have over there a1, a2, and
Right.
we also have b1, b2.
Right. But yes, but how will you remove this term? So this term we don't have any information, right?
Right. We don't know anything.
Right. So actually this thing will not work like this. So we have to do a slightly different way. So the thing
Mm-hmm.
is, so yes, up to this is fine. That okay, we can copy this part. So from here, we have that A1 is nothing but uh, MK1 plus B1, right?
Mm-hmm.
B2, right?
Right.
Now we can do the product. So A1 A2 is equal to, okay,
Yep.
B1 B2, right?
Yes.
So now everything, this part, the whole thing is divisible by M, right?
Yep.
This part is not. So then this is the remainder, right? So that's why we have. So if I subtract to the other side, so this is divisible by M, right? So M
Right.
divides this thing, right? So from here
Yep.
actually we have that A1 A2.
Equal to b1, b2 mod m.
Okay.
Yeah. Yeah.
So this is how you get the product thing. Okay.
Mm-hmm.
So this part will not work.
Yep.
Fine.
Yes.
Okay. So next is yes, but one observation is that. So suppose the thing is if we have two congruences with same modulus, so this is important. Then we can do the product. But the thing is opposite we cannot do. So opposite in the sense. Okay, let me write down. So suppose you have AC congruent to BC mod M, right? So it need not be true that A is congruent to B mod M. So you cannot cancel C from both sides like that, right?
Mm, it need not be true.
Yes, yes. It need not be true that we can cancel the C from both sides. So it may not be true.
Okay, we cannot cancel. Okay.
Yes, yes. So for an example, we can see. So if you take 15 and 2, and B you take 20, C is 2 again, modulo 10. So you can check that this is working because 15 2 is 30, right?
Mm-hmm.
30 and 40 modulo 10 work because if you subtract it is divisible by 10, right?
Yes.
But if you cancel the 2 on both sides, then what you have? 15 is congruent to
15.
20 mod 10,
And
right? But
that
this is not
doesn't
true,
work.
right? Because if you subtract it is 5.
But you could divide 10 as well.
No, so here you cannot divide it because 15 minus 20 is minus 5, right?
No, I'm saying you could divide, when you cancel 2, you also divide 10 by 2.
No, no. Here we are not saying that, right? So here, what we are saying is, if we have same modulus, m is fixed. Then if you product both side, then still m is fixed. So this works. But the
Mm-hmm.
opposite we cannot do. Suppose here we have this one is given, this quantity is given, and you cannot cancel out C and say that A and B is congruent to M. So this is
Right,
not true.
right. Okay, okay.
So this is the example what you get. Right.
Mm-hmm.
Right. One more example. So one more type of example what you have is, so it can also happen that the product UV is congruent to 0 mod M. So 0 mod M is when it is divisible, but U it's individually it is not 0 mod M, and V is also individually not congruent to 0 mod M. So that can also happen.
Okay, okay.
So for example, 6 times 4, that is 24, right? So it is
Mm-hmm.
0 mod 12. It is divisible by 12. But 6 is not divisible by 12, right? So 6 is not congruent to 0 mod 12. So neither 4 is also not congruent to 0 mod 12.
Mm-hmm.
So it can also happen like this, right?
Right. Yes.
Okay. But the thing what we can do is, in certain condition, so if we give some restriction on C, then actually this will work. So that is the next observation, right? Uh, so if the GCD of C and M, this is 1, right? Then AC congruent to BC mod M. From here, we can able to say that A is congruent to B mod M. So this we can say. So this we can say if this extra condition we have on C, that GCD of C and M is 1.
The GCD of C and M. Okay, okay.
Right.
Then, okay. Mm-hmm.
Right. So this we can see. Right. So this they have given in exercise. So when you go to exercise, we'll prove that. So for example, here it is not working in the previous example because 2 and 10, their GCD is not 1. So their GCD is 2. So that's why it is not
Right.
working.
Mm-hmm.
Okay.
Yeah.
So maybe